Right. It's a pleasure to be here. I'm actually in St. Petersburg until the end of June, so if those of you who are from St. Petersburg, I hope you can take the chance to come by and say hi at some point. This is meant to be an introductory talk to bounded arithmetic, so I see only a very small number of experts in the room, like Pavel up front, and some people in the back are going to skip out on me. And, and so this means please come on in. It's okay. So I hope you'll ask a lot of questions. I have a fair amount of material prepared, but not enough if you don't ask questions. So please ask questions. At any rate, and please feel free to move up towards the front. If you can't read my handwriting on the board, I'll use both the board and the overhead transparencies. So, good. So bounded arithmetic, this is actually a family of sort of first-order theories, and it gives a proof-based approach to computational complexity. So in particular, it gives what's turned out to be a very, very rich and quite deep way of thinking about questions about what's provable. So when the questions in computational complexity tend to be things like about what can you express, what can you compute. In bounded arithmetic and in proof complexity in general, one adds to this the question about how hard is it to prove that the expression is correct or the expression has the right properties, or how hard is it to prove that the computation is correct. And it gives us a whole other viewpoint on a lot of open questions, such as the P versus NP question and so forth. Yeah. Could I make, yes, oh, good point. Sorry, let's go, what is that, Control L? There, that's why it's better. Good, thank you. So maybe that's more readable. In particular, these theories are weak subtheories of piano arithmetic. And let me just ask, how many people have studied piano arithmetic in the room? 3 or 4 people? No, half of you? How many people have not studied anything about piano arithmetic? How many people are not sure? How many people aren't sure if they're not sure? Okay. Oh well. Okay, you don't need to know any piano arithmetic, but it might help motivate a little bit some of the beginnings here. So basically, these are weak theories where we restrict the induction axioms in very strong ways to a feasible kind of induction. I'll get into the details of this in a minute. The theories we're working with have very close connections to feasible classes of computation, such as polynomial time, or near feasible classes, such as non-deterministic polynomial time, or p-space, and so on. They have very close connections to propositional proof systems. So this is logic dealing with just what's valid tautologies. And in fact, bounded arithmetic can be viewed as a uniform version of propositional proof complexity. And they have, as I mentioned already, they have very close connections to a lot of these open questions, such as the P versus NP question. So all these are interesting reasons to study them. Okay, how am I doing on time? Going too fast already. So let me just dive right into some of the technical stuff then. The bounded arithmetic theories are theories of the integers. So these are first order theories. We have variables like x, y, z that range over integers. By this I mean the non-negative integers. We have function symbols, the same ones that you see in piano arithmetic, 0, successor, plus, times, less than or equal to. And then we have some additional ones that are useful for the theories that we're talking about here. The length of x means the length of the binary representation of x, so just the number of bits used to write out x. 1/2 x means just what you would expect, rounded down to the nearest integer. X smash y is this sort of interesting thing, which I'll talk more about. It gives you a polynomial growth rate. X smash y is 2 to the length of x times the length of y. In particular, the length of x smash y is the same as the length of x times the length of y plus 1. Just because the length of 2 to the I is I plus 1, because it consists, 2 to the I consists of a 1 followed by I many zeros, right? Okay. MSP is another helper function. It gives us MSP of xi is x divided by 2 to the I. So it chops off the low order I many bits of x when it's written in base 2 notation. And the purpose of these things are, over piano arithmetic, is the smash function is particularly important because it gives us polynomial growth rate functions. So this lets us get a connection to polynomial time computability. MSP is going to be helpful for bootstrapping methods. That's more there for technical reasons. It makes it easier to do sequence coding. So I'm talking about Gödel beta functions for sequence coding. And then the length of x and 1/2 x are very important for us because they sort of facilitate writing out these feasible forms of induction in the next few slides. Okay, so those are important for that. Since I didn't get people to raise their hands before, how many people know what I mean when I say Gödel beta function and sequence coding? Nearly everybody? Half of you? Okay, all right. Okay. So the syntax here, so to start from the very beginning, we can form, terms, like x plus 7 times y smashed with z would be an example of a term. Formulas are built up with Boolean connectives and or not, quantifiers for all exists, and in bounded arithmetic we have these special quantifiers. Exists x less than or equal to t phi, which means that there's an x less than or equal to t, right? That there is an x less than or equal to t in phi, right? And then also for all x less than or equal to t phi. And these are called bounded quantifiers. When the t is of the form the length of something, so we put these, if we have lengths in here, right? These are called sharply bounded quantifiers. So the bounds are sharp, they're stricter. So the idea being that we're looking at a smaller set of x's. In particular, as I'll describe more, when you have, does there exist an x less than or equal to the length of t, you can search efficiently, quickly for x's up to the length of t in effectively in polynomial time. So a sharply bounded quantifier becomes a polynomial time operation. And now we then make a hierarchy of formulas. The sharply bounded formulas are called sigma b0, b for bounded, 0 for no non-sharply bounded quantifiers. These are the same thing as a pi b0 and delta b0. Sigma b I plus 1 is then defined by adding existential bounded quantifiers onto pi bi formulas. Pi bi plus 1 would then be defined dually. So if I had a formula like exists x less than or equal to t, exists y less than or equal to t prime, for all z less than or equal to s, phi, if phi is sharply bounded, okay, then since nobody's asking me a question, I'll ask you a question. What is the complexity of this formula? In this terms of this sigma or pi class is here. Sigma b2, yes, very good. So this is sigma b2 because we've got a block of universals and a block of existential quantifiers. So that's the 2. The outer thing isn't exists. So that's the sigma. Okay. Okay. So let's see, what's on the next? Yeah.
Why do you use the term arbitrary sharply bounded quantification? So sigma b.
Arbitrarily, arbitrary, good question. I'm referring to the fact that actually I could insert in here, for instance, for all u less than or equal to the length of r. I could stick that in there. It would still be a sigma b2 formula. Okay, very good question. So we just ignore the sharply bounded quantifiers wherever they exist. Now we will later on put special forms on these things and show you don't need to have sharply bounded quantifiers out in front. But for now, we allow them just anywhere. Okay. And we're really interested in just putting them in pre-next form for this, yeah. Was that a question back there?
I'm not sure if I still understand the sharply bounded. You're saying for all x of the size of x itself is less than the size of?
No. That's a different thing. So there's two kinds. If I wrote exists an x such that the length of x is less than or equal to the length of t, okay, ... that would mean the same thing as something like there exists an x, well, I could say less than 2 times t such that the length of x is less than or equal to the length of t, and, I'll use the other and sign, and ... I could simulate this quantifier, but it's a bounded quantifier, but not a sharply bounded quantifier, right?
I'm not sure how sharply bounded that is.
Okay, so the idea would be, suppose you have some property like, exists an x less than or equal to a, such that phi of x a, and let's say that this is a polynomial time property. Okay. In particular, a delta B0 property, a sharply bounded formula, is polynomial time. But the point is, if we have put the lengths on there, okay, we can search for an x just by running through all possible values of x from 0 up through the length of a. And that'll be a polynomial time operation. So this is all polynomial time. So in particular, any sharply bounded formula is polynomial time. Okay. Question, yeah.
So if you want to keep sigma b2 there, you cannot put the quantifier like in between the existentials, right?
Oh, yeah, because it's sharply bounded, it's okay.
It goes anywhere.
It can go anywhere, yeah. So we're just going to ignore those quantifiers.
Oh, because they allow this
Yes.
fast search that you
They allow this fast
can
search.
just remove them.
You can effectively remove them. Actually, we'll maybe get a little ahead of ourselves. There's a quantifier exchange property that says you can push sharply bounded quantifiers past the other bounded quantifiers. Okay, so I should probably do that a little bit later, but okay, but yes. So, but let me, again, to write this out all the way, for all u less than or the length of r, exists x less than or equal to t, is still sigma b2. Right? We just ignore this sharply bounded quantifier just by the reason that it's sharply bounded. We only look at the existential bounded quantifiers and the universal bounded quantifier. Okay. Okay. And the crucial property here that we're going to use is that, well, one crucial property, I'm not really going to use it, but any sigma b1 formula, say phi of a, expresses an NP property. Okay. Because you can evaluate these things in non-deterministic polynomial time just by existentially guessing the values for the existentially quantified variables. And the sharply bounded quantifiers, you can just loop through all possible values. Okay. And likewise, any delta B0, which is the same as sigma B0, I'll usually call it that way, and pi B0 as well, formula, it expresses a polynomial time property. Okay. Okay. Other way? What about the other? Actually, every NP property can be expressed as a sigma B1 formula. The other direction here is probably not true, I guess, because this is a pretty weak class of things, right? Yeah, okay. But later on, we'll be adding them in anyway, and I could have just added them in to start with, but we don't usually. Okay, another question.
So
No.
when you say, what's the difference between bounded and sharply bounded formulas since you don't have any quantifiers?
Sharply bounded means only sharply bounded quantifiers.
But a formula doesn't have any quantifiers, right?
No, a formula is allowed to have quantifiers, yeah.
So the formula is also allowed to have.
So formulas, so again, we have, formulas are built up out of terms. Okay, so terms are built out of function symbols. Formulas are then built up out of equals, out of less than or equal to, out of and or not, and out of for all and exists. Okay, Now, we're not going to allow the unbounded quantifiers, the usual ones. We're only going to be allowing the bounded quantifiers for the most part. And the bounded ones, we then distinguish. There's the bounded ones and there's the sharply bounded ones. Yeah, okay, yeah.
And there are some restrictions on the t.
Oh, the restrictions on the t. The main thing is if you have exists x less than or equal to t, x can't appear free in t. You can't say something like exists x less than or equal to x plus 1 or something like that. That'd be cheating. Okay. Okay.
Question.
Yes.
So doesn't sigma b 0, how does it compare with tc 0?
How does sigma b0 compare with tc0? Okay. So tc0 is bounded depth where you have counting gates. Seems to be a much stronger thing, right? I don't know if that's a theorem though. I think
this looks like bounded circuits with
it's like
AC0 where you can also
do Oh yeah, so it's AC. Oh, good point. Well, good. Yeah, this is a good question. So these bounded these sharply bounded things look like AC0, but we have multiplication in the language. Multiplication does give you counting. Not sure if that's enough to give you nested counting gates the way TC0 would or not. So multiplication gives you counting. You can look at the middle bit and so on. This is getting beyond what I wanted to get into, I think, at this point. But yes, it's a good question. Yeah, I'm not sure. Yes?
So if your form, do you allow for free variables?
Yes, there are free variables. There are the usual distinctions on free variables and bound variables. The bound variables being the ones captured by quantifiers. Yeah.
Okay, but if I were to think of it, the existential closure of the free variables, would they also have bounds on them?
The free variables are usually, if you prove something like, later on if we prove something like phi of A and A is free, that's the same as proving for all A phi of A. Okay.
There, for all quantifier is unbounded.
Yeah, the for all, but we don't have to write the quantifier there. We just prove it for an arbitrary A. Okay. Okay. All right. So I think we've actually done this slide here. Oh, let's see. So thank you for asking all the questions on the slide ahead. Let's see if you can pull it off again. I guess I didn't mention here that we didn't get to this one. The terms all have polynomial growth rate. So this is because this is true of the base functions in the language, and it's why we threw smash function in, was to make it be of this form. The length of any particular term, and term means built out of plus, successor times smash, 1/2 MSP in length. The lengths of those things are all polynomially bounded by the lengths of the arguments to them. So we're getting polynomial growth rate here. And I think everything else we said here, except you can sort of ignore pretty much the last part, is if you happen to know about the polynomial time hierarchy, the predicates expressible at the ith level, sigma pi of the polynomial time hierarchy, are exactly those things definable by sigma bi formulas. Okay. That's true at NP. It's not too hard to show. It's a pretty straightforward thing, especially with our language having things like MSP in it. Okay, so good. Did that slide. Why include the smash function? I already partly covered this one. Let's see. Gives terms of polynomial growth, but two other things. One is it gives growth rate convenient for arithmetization of metamathematics. So this is one of these arithmetization of metamathematics. This is the kind of phrase that should roll off your tongue and make you sound very impressive. But that's just, how many people have seen Gödel's incompleteness theorem? The same, oh, more people. Oh, good. Very good. So one of the important things, if you remember in that, is the substitution function, which is something like sub, and we take a formula, Gödel number of a formula, the Gödel number of a variable x and the Gödel number of a term, and it gives you the Gödel number of replacing x with the term, right? And so if you think about this, if there's n symbols in phi and there's m symbols in t, then this has something like n times m many symbols. Okay, and so this is, in other words, the length of the formula after the substitution is bounded by the product of the lengths of the inputs to the thing. So that's the kind of growth rate you get out of the smash function. So without the smash function, this kind of function would be very difficult, maybe just impossible to define. Okay. well, certainly as stated, it would be very difficult to do. So you would lose a lot of the sort of basic stuff that's done for arithmetic for that. So that's a good reason for the smash function. And the other one is we brought up this question that was touching on the quantifier exchange property. So let me address that now. Quantifier exchange property, here we say the following. If for every x less than or equal to the length of t, so there's a small number of x's, there's a y less than or equal to s, so it's not sharply bounded, such that property A holds. Then there's a single w with a bound given here, such that every element less than t, you think of w as encoding a sequence. W sub x is the xth member of the sequence. And so the xth member of the sequence satisfies A. And I guess I should have added on here, and w sub x is less than or equal to s. Okay. And the smash function is exactly what's needed, because think of each y is encoded with length of y many bits. Length of s many bits, and there's length of t many different y's to encode. So we need length of s times length of t many bits to encode them all together. And the smash function is exactly what we need. And that then lets us push the sharply bounded quantifiers inside.
Sorry, my question, and if there is x in S, how can we write this?
Yes, if there's x and s, how can we write this? So here, that's a good technical term. There's always, in fact, I think it's true for the functions in the, well, not quite true. We always have, we can easily build a term s star of x, which is greater than or equal to s of x, by leaving out a few things like MSP. By, we can get a bound that's bigger than s with some other term. Usually just s and s star works for most of the functions. I think MSP in its second place might be an exception. So we can, and then we just say that, so that means that if we just use s star of t instead of s, so just replace this s here, y less than or equal to s, by s star of t. S star, yeah, star the length of t works. Actually, you could do either one, right? But s star the length of t. Then we know that because the y's are all less than or equal to s of x, and s is less than or equal to length of t, then the y's are all less than s star of the length of t. So we can just put a uniform upper bound on the y's, in other words. Good question. Okay, just trying to gloss over those kind of details, but this is great of you to bring them up. Yeah. Yes?
You said that all the functions that you have included have polynomial growth rate.
Yes.
But there could be functions that have polynomial growth rate but cannot be written in terms of these functions.
Yes, for sure. Yes. Yes. For example, non-computable function. Okay. Okay, so these are three reasons for smash. Okay. So now I get to axioms. So so basically we have some rather simple kind of axioms I don't want to worry about details of, but just basic quantifier-free things giving the properties of the symbols. So for instance, the associative property of addition, x plus y plus z equals x plus y, quantity plus z. Or if you're familiar with Robinson's theory Q, axioms from that, though, x plus 0 equals x plus successor of x equals successor of x plus, x plus successor of y equals successor of x plus y. And then also for these other things like MSP. Remember, MSP was dividing by 2 to the I. So MSP of x, SI means I plus 1. That's the successor of I, is 1/2 of MSP xi. Okay. So these are quantifier-free formulas that just describe the basic properties of the function symbols. And then our crucial ones are the induction axioms. So the induction axioms, the usual induction, so I've got a class of formulas phi. I'm going to restrict A to be a phi formula. So like the sigma b1 formulas, for instance. And the usual induction is what's stated here. If A of 0 holds, and if for every x, A of x implies A of x plus 1, then for every x, A of x. Okay. I'd ask how many people have seen induction, but I think the answer is everybody. Okay. Okay. How many people have taught induction? Nobody. Okay. Oh, one person. Good. Okay. So then there's the so-called length. Let me skip p induction for the moment. Let's look at length induction. So length induction says for all, if A of 0 holds, and for all x, A of x implies A of x plus 1, then for all x, a of the length of x. Okay, so is this, let's start off with, so it's length induction because we're doing induction to the length of x rather than to x, right? So the first question is this stronger than the usual end induction or weaker than the usual end induction or the same?
Wouldn't the end induction imply that?
End induction implies this, absolutely, because if for every x, a of x, then certainly for every x, a of the length of x, right? What about the converse? No, sorry, does for all x, a of the length of x imply for all x, a of x. So remember, length of x is the number of bits in the binary representation of x. So it's approximately equal to log base 2 of x. In fact, it's exactly equal to the log base 2 of x plus 1 rounded up to the nearest integer. Okay.
Doesn't imply a of 0.
Well, let's see. I didn't tell you this. Special case. So that's actually one of the basic axioms. I didn't tell you that part. Very good. Yeah, what is the log? Well, yeah, I guess the length of 0 would be 1 if you think about the number of bits. But we strip off all leading zeros, including on 0 itself. Okay. So, okay, I mean, you got a 50-50 chance of being right here. So I hear a yes. Okay. And the other question might be, well, why did I bother? The other thinking should have been, why do I have a separate axiom if the answer is yes? So the answer should be no, or otherwise it wouldn't be a separate axiom, right? So in real life, we can think of the length function as being injective on the, let's say, the positive integers, okay? On the non-negative integers with this thing, right? But for us, and this is because it's surjective. Surjective. So that since the function x maps to 2 to the x is total, right? Okay. But for us, so these facts are not provable in theories of bounded arithmetic. So the axioms are not provably equivalent. Okay, so although in real life nearly all of us believe that the exponential function is total and the length function is surjective, I occasionally meet people who don't believe this, but it's a very rare event. Okay, but these facts are not provable in our theories they're working with. So you should really enter this alternate reality where the exponentiation function isn't total and the length function is not surjective. And so if you get into this mode long enough, you start to believe it. Okay. But they're different for that reason, okay? Likewise, quantifying, for all x less than the length of something is a very different thing than for all x less than without the length on it. Okay, so that's L induction. P induction, let's come back to P induction. P induction tells you the following. If a of 0 holds, and if for all x, a of 1/2 x, then a of x, then for all x, a of x. So this is like induction on the length of x rather than induction to the length of x. And so the general setting is that P induction and L induction are equivalent. And the kind of example I like to use is, first of all, it's not even clear this axiom's valid. Is P induction valid? Is it actually a true statement? It looks a little strange. We're not going from x to x plus 1. We're going from 1/2 x to x. But the point is, yes, it's valid because if the hypotheses are true, there can't be any least x where a of x is false. So if a of 0 holds and if for all x, a of 1/2 x implies a of x, there can't be any first x where a of x is false. And more generally, the kind of thing I usually, suppose you want to show A of 100 from A of 0 and for all x, A of 1/2 x implies A of x. Okay, well, you would just start with A of 0 and you'd say, therefore, A of 1, because 1/2 of 1 is 0, rounded down. Therefore, A of 3, therefore, A of 6, I guess is next. A of 12, A of 25, A of 50, voila, A of 100. Okay, and so you would just, by using this, repeatedly using this hypothesis here, you would go from A of 0 up to 100, in this case in only 7 steps. 7 steps, right? And so the number of steps that it takes to get from 0 to 100 is equal to the length of 100, right? So in particular, to conclude A of x from the hypotheses of P induction takes length of x many steps. Okay. So this is the P induction axiom. So P for polynomial. Okay.
Quick question.
Yes?
So the fee that you're talking about here are the fee from bounded arithmetic, not arbitrary fee, right?
So I haven't yet said which class's phi I'm working with, but I'm going to work with things like sigma b1, for instance, for my class phi.
So because earlier you gave an example where phi int and phi L int are not the same. The example with the exponentiation function.
Phi int.
You said that you could prove.
Oh, yeah, phi end. Yeah, the example was phi. So he's the comment. End seems to be different than L end, right? Yes,
Right.
because.
But there you talked about the exponentiation function, which you cannot represent using just polynomial, the functions that you have.
Right. So yeah, so here he's asking about, is the same kind of thing happen here between pinned and p end and lin? And so no, these two things are provably equivalent. These two forms of induction are each can be proved from the other in the systems we're working with. So one is induction to the length of x, the other is on the length of x. So you can prove the equivalence. And I have that on my next slide. No, I don't. There it is. Oh. Yeah, so here, one slide ahead, but let me do the previous slide first. I'll probably skip. How am I doing on time, by the way? Let me give the basic definitions, or the fundamental definitions. So we're going to be working with these theories SI2 and TI2. In particular, I'm going to be most of the time about I equals 1, so don't worry too much about the I part of it. They're axiomatized as follows. You take these basic axioms that give you the basic properties, and we have P induction for sigma bi formulas. TI2 is the basic axioms plus ordinary induction for the sigma bi formulas. And then we take the union of these theories as S2. This would be, S2 would thus have induction for all bounded formulas, right? Any sigma bi formula for any I. T2 would have normal induction for all bounded formulas. And as a comment here, this theory was introduced earlier by, well, Parikh without the smash function and Wilkie Paris with the smash function, and very different guys before that. That's for the experts. And just looking ahead, the picture is going to be that S12 is a subtheory of T12 is a subtheory of S22 in a way I'll describe later on in a sort of hierarchy of theories. But I'll talk later about where that comes from, just to sort of get you oriented. So in particular, what I really will talk the most about for the first part of the lectures is S12. So S12 is the basic axioms plus sigma b1 P induction, or equivalently, sigma b1 L induction will actually be equivalent. And essentially, this is P induction on NP predicates. Because the sigma b1 formulas express exactly the NP properties. So we're doing induction, feasible length induction, P induction, but on the NP predicates. Okay. So actually, I was going to quickly prove S12 is a subtheory of T12 for you, or maybe I'll just show you on the slides. And I'll do it. Why not? And Here I say it's equivalent. Well, yet requires a proof. Right. So this can be proved to be equivalent, I should say, right. Okay. Can be proved to be, so can be proved.
But it's only for one, for sigma E1.
Oh, no, I'm trying to keep things simple. So it's equivalent for all I. Okay.
I see. But in the slide,
The slide says for all I, yes. Okay, yeah. Okay, yeah. So mostly I'm.
slide was a subset equal, not equal.
It's induction.
Is there something? What I'm missing the question? This one. I see. Whenever I write either subset without the equal sign there or subset with the equal sign there, I mean with the equal sign. Okay. Usually I just leave it off. Somehow that got left there. We don't know if these theories are different or not. They could all be equal. So we don't know whether P equals NP. We don't know whether these theories prove P equals NP. If they do, everything collapses away. So, we're living in this world of where this big edifice of things we've created, it could all collapse down to be just the same thing.
But here you something I don't understand. Here you say it's the same, and here you say you don't know if it's the same.
Which is the same. Here I say that
T1, 2 is equal to S to T1, 2.
L induction.
Oh, sorry.
Yeah, T1, 2 has the induction, yeah. Yeah. Oh, whoops. Okay. Okay. So I guess every talk deserves a proof in more or less full detail. So it says sketch nonetheless, so you have to bear with me if it doesn't quite make sense. So this is basically enough to show, what I'm showing here is that S12 is a subtheory of T12, or SI2 is a subtheory of TI2. And basically here's the argument, is you want to prove P induction for A of X. So to do this, let's take a new free variable C. Instead of the for all X here, we just put an arbitrary A of C here. We're trying to show this. We take B of I to be the formula A of some term T of I, where I is the term MSP of C, C minus, length of C minus I. So B of I is the formula A of C divided by 2 to the length of C minus I, rounded down. And then we have that B of 0 is essentially the same as A of C. B of length of C is the same as, I should say it's just equivalent to, and this can be proved here, to A of 0. And the induction hypothesis for A, that for every x, A of 1/2 x implies A of x, gives us exactly the needed induction hypothesis that for every I, B of I implies B of I plus 1, because T of I is 1/2 of T of I plus 1. Okay. So I don't want to spend a huge amount of time on this, but if it hasn't made sense yet, trust me, it should make sense. Okay, either that or I made a horrible mistake on the slide. But I guess not. No one's raising their hand. Okay. So this is how, and the point here is L induction is clearly a consequence of induction. We discussed that before. And by this argument here, P induction is a consequence of L induction, so thus SI2 is a subtheory of TI2. You can also prove the converse of this lemma as well, that L induction follows from P induction by about the same kind of proof. Okay. That's actually a little harder the other way. Okay. Okay. All right. So what's next? Provably total functions. So we're interested in the strength of these theories. In particular, we're interested in what things can be proved total, what functions can be proved total. By the way, I forgot already. I started at 1/4 is that right?
Yes.
Yes, okay, good. Okay.
20 minutes.
Okay, so the first definition is more motivational. We're not actually going to really use this one. We'll say R, a function f mapping integers to integers. I use boldface n for the non-negative integers. it's provably total in a theory R. So R is one of our theories like SI2 or S12 or T12 in particular. If there's a formula, a two-place formula, A sub f, I call it, of xy, which satisfies the following properties. First of all, that A of xy is true if and only if x equals y. So it defines the graph of the function f. Secondly, that R proves that for every x there is a unique y, A of xy. Sometimes we'll drop the uniqueness property, but for now, this is just for mode. This is what we want to have. So R proves that for every x there's a single y such that A of xy holds, and we'll add on the condition that A is polynomial time computable. Okay, so this is what I mean by provably total function. So we're interested in characterizing for a given theory what functions are provably total in the theory. For instance, all our theories are going to be able to define the polynomial time functions. So let's step back a little bit and be a little more technical. We'll say that a function f is sigma b1 definable by R, provided there's a sigma b1 formula A of xy, such that R proves, well, first of all, that for every x there's a y, and just to make life easy, I'm going to put a bound t on the y, such that A of xy. Usually we get the bound t for free, but let me just put it there explicitly. And then R also proves the uniqueness property that if there's a y and a y prime, such that both A of xy and A of xy prime hold, then y equals y prime. So there's at most one y. First one said there's at least one y. Second one says there's most one y. And thirdly, that A defines the graph of f. Okay? Then we say that it's sigma b1 definable by the theory R. Okay.
Why did you put the AF as polynomial time computable?
Good question. So we're really interested in sigma b1 for several reasons, but the point is here, I've got this theory R. It's going to prove for all x there exists a y less than or equal to t. And now here I've got some sigma b1 property. And so this has the general form, there exists a z less than or equal to s, and then some property b of xyz, which is polynomial time. Okay? This is the general form. So we can think of this saying again that R proves that for all x there exists a pair yz less than or equal to some bound of, I guess, s times t more or less works, right? Say s times t squared just to be safe, such that phi of x, y, z. So what does this mean, a pairs? I mean a single number encoding both numbers y and z, right? Say the lower order bits encode z and the upper bits encode y. So now this becomes a polynomial time thing, okay? So we're back to a provably total function in the first sense, because for every x there's a pair yz, which then satisfies a polynomial time property.
But my understanding is that if you put this restriction, it makes the property of provably total more flexible, in the sense more inclusive of more functions. If you take it out, it will still subsume the previous.
This one, if I take out this condition, so I guess if I take that property out, there's possibility of defining more functions. In particular, we will also look at the sigma bi definable functions, where the property is a sigma bi property, so at the ith level of the polynomial time hierarchy. This permits defining more functions. But we want to avoid silly stuff like R proves for all x there exists a y. If there exists a z such that, say, z equals 2 to the x, then y equals z. This would be a silly sort of definition of y as a function of x, because I could really sort of put almost any property here I wanted to. And I wouldn't have proved it existed. I would just say if it exists, right, then y is equal to it. And so you wouldn't really be proving the existence of anything in any meaningful way, right? So I want to avoid that kind of thing. Okay. Now this is a really important definition for us, and of course, everything I say is going to work for all values of I in some way or another. I'll say that, but to keep life simple, and it's really the most interesting case also, is let's just look at the I equals 1 case. Okay. Okay. So the important thing here about this is then that any sigma b1 definable function, question first, good.
The previous slide, so is there any bound on that term t, or what's that?
This term t here, so t is the bound. So t is in the language of bounded arithmetic.
Fixed or
T is, yeah, we're saying that there's a particular formula A, a particular formula T, a particular term T, and R proves this thing, yes, right.
sorry.
In particular, in general, T is going to be involving just x, and so it's going to be less than or equal to 2 to the p of the length of x for some polynomial by the growth rates, right? Yeah, but that's an important thing. We've got a particular proof in the theory R of this fact. We've got a particular term T, a particular formula A that we're working with. That's actually pretty important. Okay, it gets even more confusing. That point gets more confusing if you're not careful. Okay. Other questions? Marco.
What precisely do you mean by A sub f is p-time computable? Do you mean like given the 2 I can check it in p-time?
Yes. Yes, so the question, what does A sub f p-time computable mean? It means given x and y, there's a polynomial time method to check whether A of xy holds. Right. Okay. All right, so then here's a important thing for us, just still getting started though. If you have a sigma b1 definable function, we can add it to the language and use it freely as if it were one of the original built-in function symbols. We can use it in induction axioms. It doesn't count towards our quantifiers. And in particular, already our smallest theory, S12, can sigma b1 define every polynomial time function. So we could actually just include, we started off with these functions, 0, successor, plus, times, and so forth. We could have added every polynomial time function to that and not really change our theories in any essential fashion. Okay. So this is the base. So this is an important thing for us. It's just getting started. In fact, part of the way the theories had to be designed for this theorem to hold. Otherwise, I would have defined them to be stronger theories to make this hold, right? Okay. Okay. So this is one of these, theorems by construction, right? Theorems. Okay.
Maybe you can explain what is conservativity.
Oh yeah, conservativity. Yes, I should do that. Thank you. So what I mean here is that, actually several things. So we'd have let's say S12, sigma b1 defines f of x equals y using some formula A of xy. So that, and in particular, using the statement that for all x, there exists a y less than or equal to t, A of xy, y. Okay. What I mean by conservativity is several things. First of all, any formula in the original language which is provable. So if S12 with this new function symbol f added to it, so let's use this notation. I have sigma b1 defined a function. I take this function symbol and I just add a new function symbol to the language, and I give it the axiom that f of x equals y if and only if A of xy. Oh, and y less than or equal to t, I suppose. Okay. So this is the defining axiom for f. And then the point is, any formula, if S proves it, S12 of f proves it, then already the original theory proves it. So if the new and large theory proves some formula in the original language, then already the original theory proves it. Okay. And the other comment is actually more than that is true. If I have some formula phi and it's involving f of x someplace inside of it, let's say let's do some other more general thing, f of r for some term r. Suppose I have a formula t that's involving f of r, okay, in the bigger language. I can re-express this as there exists a y A of ry and phi of dot 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 y. Okay, and I can actually say there exists a y less than or equal to t. And this means the same thing, and it's expressed in the old language. So anything that's expressed in the new language using f can be re-expressed in the old language not using f. And then the kicker is you can also here I brought in an existential bounded quantifier, which sounds a little dangerous, but you can also write it as for all y less than or equal to t, if A of ry, then phi of y. The point being, for any given r, there's a unique y such that A of ry holds, right? Because that was what it meant for S12 to sigma b1 define it. There was a unique y. So either you could say there is a y that has that property and phi holds, or for every y, if it has that property, then phi holds. Since there's exactly one y, they both mean the same thing. So we can actually use either for alls or exists when we get rid of function symbols. And in this way, we can always sort of never increase the alternation of bounded quantifiers because we can always just choose the for all or the exists correctly to keep the quantifier alternation the same as it was, right? Okay, did I answer your question? So does everyone know what conservative means now? That's the other question, yeah. Conservative just means it doesn't prove anything new. You add it in, the theory is essentially no stronger than it was before you put the function symbol in. And in this case, it actually means more. Not only that, the theory can't even express anything new over what it could already express beforehand. Okay. Okay, so I want to talk about next goal is here is this converse. S12 can sigma b1 define every polynomial time function. The converse is going to be that every sigma b1 defined function is polynomial time. Actually, before I do that, let me just mention, why don't I just skip this? Okay, here we go. Okay, so the converses of this last theorem holds as well. So just look at the top theorem. This is the so-called main theorem for S12. Suppose f is sigma b1 defined by S12, then f is computable in polynomial time. So in fact, S12 can prove give explicitly a Turing machine that computes f, prove a polynomial bound on the runtime of the Turing machine, and that its output is f, and so forth. Okay, and so the general idea then, this shows that S12 has proof theoretic strength corresponding to polynomial time computation. Okay. Cool. All right. So questions about what the theorem means. This is a main theorem, so this is not where you check out saying it's only 7 minutes until coffee and I don't know what, cookies or something like that, so you can hold on for it. Questions about what this means.
Can you go back one slide?
Yes, I can go back one slide. This one I missed, or the one before this?
No, the one before.
Yeah.
So you're saying any single. Actually, one question I had was, you said, can we introduce conservatively?
Right. So introduce conservatively. The question is again about this, right? What does this mean?
Yeah.
So what it means is that you can introduce it conservatively. When you introduce it, we add the new function symbol, and we add this new axiom just saying that it's the f of x equals y if and only if a of x, y. And the claim is then, this doesn't allow you to prove anything new. Not only that, it doesn't allow you to express anything new. Anything you could express with the new function symbol could already be expressed without the new function symbol. So it's a very inessential kind of extension of the theory.
What would be an example of a non-conservative extension?
What would be an example of a non-conservative extension? Let's see, what's the best example? Well, something defining say something defining whether SAT, take an instance of SAT, doesn't have a satisfying assignment. So just a yes-no answer deciding SAT. It's probably not conservative over adding that in, unless, of course, P equals NP, in which case it is possibly conservative if S12 proves P equals NP. Okay, so just like the function that take f of something that says is equal to 1, if it's a satisfying formula, a satisfiable formula equal to 0, otherwise would presumably not be a conservative extension. Okay.
The converse that you talk about in this theorem here
Is this one. This is the converse is the main theorem, yeah. Okay. So let me say a little bit about the idea of the proof here, but not too much. So probably I won't get to it says at the bottom of the next 3 slides, spell out more details. I probably won't do those. So the proof of the main theorem uses a witnessing argument. So what it does is we work in the sequent calculus. How many people have seen the sequent calculus? Okay, pretty good swath of you actually. Okay, okay. So, and we apply a cut elimination argument to say that every formula in the sequent calculus proof is sigma b1. And then once you do that, the sequent calculus proof can then just be read as a program for computing the function f. You have a proof in which every line is sigma b1. The last line just says there is a y less than or equal to t of c, a of cy, and c is what x used to be, right? And if you just go through the proof, it's a program along with a proof of correctness for computing y as a function of c. And the program has polynomial runtime, and the p inductions in the proof correspond to for loops in effect. The p means that they're polynomial length iterations on the for loops. So you come up, there was this question about particular terms and so on. We have a particular proof. We hit it with cut elimination. We have another particular proof in which every formula is sigma b1. This particular proof has a certain number, constant number of induction statements in it. Think of those as being nested for loops. The nested for loops are nested to some depth. They're each polynomial in their length. And then the whole thing is polynomial time. So that's the picture of the proof. I guess I can go very quickly through some details, but really here, this, if you want to check out for the proof, that's okay. Let's see. So a couple details. To make life easy, we put formulas in this sharply strict form. Sharply strict means you have one existential quantifier, one for all, blah, blah, oh, well, this is a general thing. Sharply strict sigma b1, let me just do that, since I'm just doing the I equals 1 case. SS sigma b1 means formulas of the form exists x less than or equal to t for all y less than or equal to the length of s, a sharply bounded quantifier, phi, where phi is quantifier free. So we can get a proof in which every formula has this strictly sharply bounded, too many sharps in there, sharply strict formulas, okay? Okay. And the point here is that this proposition is basically saying is that we could actually do induction just on these things, and we could get the same theory. We could have restricted our induction axioms from the beginning to be just on these particular formulas, and with some care, you can show that it all works out. And this means that you can form the sequent calculus proof in which every formula has this form. And we need one more thing, of notion of a witness. How am I doing on time? I really don't want to go over by much. 1 minute, all right. So the idea of a witness, we say that a value u is a witness for one of these statements. If you have an exists x less than or equal to t, u is a witness for it if u gives a value for x. Okay. So the witnesses are just values that for the x that say that this formula is true. And then the final thing, and again, I will literally take 30 seconds, the witnessing theorem just goes back to the sequent calculus and says if you have a sequent of formulas, gamma arrows delta, and you have things, so what does a sequent calculus mean? Oh boy, where's my eraser? So the point is a sequent has the form gamma arrows delta, and this means a set of formulas gamma 1 through gamma k implies delta 1 through delta L. These are just formulas, right? So gamma 1 through gamma k are all formulas, delta 1 through delta L. They're all strict sigma b1 formulas, in fact. And this means the conjunction, a sequent means the conjunction of the gamma i's implies the disjunction of the delta j's. If you've seen the sequent calculus, that's just what this means. So there's commas here separating these gammas. The commas mean ands on this side, they mean or on that side. And the witnessing lemma just tells us that there's a polynomial time algorithm, so which given witnesses for the delta j's produces a witness, gamma i's, and this should be an I here as well. So we have and of gamma i's implies the or of delta j's. If we're giving witnesses, these are these u values for the gamma i's, the polynomial time algorithm produces a witness for one of the delta j's. And this is basically you go through the lines of the proof, and the p inductions then are the for loops, and I said everything else is just simple polynomial time operations. That's all I was going to say. So that was the rushed version of my rushed version of the proof here. But I hope I got the idea across. We're going to stop. Should I stop here? Yes. There are some things that generalize upwards, but let's not worry about it. Is there a question?
I think it's important to say, when I was reading this a long time ago, that there is distinction between something that is conservative and something that is conservative and can be applied in induction.
Yes, that's a good point. So yeah, I said that, but you're right, I should have stressed this more. It's not only conservative, we also have induction for the formulas that involve the new f's. So that's an excellent point. I should have said that better. So we add these new polynomial time functions. We treat them as atomic symbols as if they're in the original language, and we're allowed to do induction on them. And the reason this works is because of this quantifier properties I was talking about earlier. Yeah. Thank you. Yeah. Marco.
If you throw in like counting quantifiers instead, do you get like the counting hierarchy?
People have worked with counting quantifiers. It hasn't been, you can certainly express exactly the counting hierarchy. No one's extensively studied bounded arithmetic with counting quantifiers. People defined it, but maybe you have a couple experts here who maybe remember something I don't, but you can certainly define it that way, and you do get the counting hierarchy in terms of expressibility and so on, yeah. Okay. All right, time for break. Other questions? Okay.